Chapter 19, Text as Data, Text Mining, and Sentiment Analysis. Text is a vast source of data for business. Examples are earnings announcements, communications to shareholders, press releases, restaurant reviews, political speeches in Congress, and Supreme Court opinions, and so on. Text data is extremely high-dimensional. The analysis of phrase counts from text documents is the current state of the art. The bag of words representation of text assigns frequencies to words or combinations of words. However, considerable pre-processing of text is needed before one can obtain frequency information on words and before one can start the statistical analysis. Information retrieval and the appropriate tokenization of the information are very important. The first step when faced with a raw text document is to stem the words. This means that one cuts words to their root. For example, tax, from taxing, taxes, and taxation. The Porter stemming algorithm, named after Martin Porter, has become the English standard. It is an algorithm for removing common morphological and inflectional endings from English words. The next step is to search the text documents for a list of stop words containing irrelevant words marked for removal. If, and, but, who, what, the, they, their, a, or, and so on are examples of stop words that need to be removed. But one needs to be careful because one person's stop word is another's key term. Also, one usually removes words that are extremely rare. Imagine one wants to compare all of Shakespeare's plays. A play is referred to as the document, and the set of all plays is referred to as the corpus. If a certain term occurs only once, it will not be useful for comparing documents. A reasonable rule removes words with relative frequencies below 0.5%. More sophisticated removal rules have been considered in the literature. For example, in a corpus of n documents, for example, all of Shakespeare's plays, one can base the screenings of words on the TF-IDF, which is the term frequency inverse document frequency score. That is, Fij times the logarithm of n over dj, where the term frequency of Fij is the relative frequency of word j in document I. Its frequent count divided by the total number of words in that document. N is the number of documents. dj is the number of documents containing word j, and the logarithm of n over dj is the inverse document frequency, or the IDF. One omits all words with the TF-IDF below a certain threshold. Example 19.1. Consider a document containing 10,000 words, wherein the word donkey appears 300 times. Following the earlier definition, the term frequency for donkey is 300 over 10,000, which is 0.03. Now, assuming we have 1,000 documents and donkey appears in 10 of these, then its inverse document frequency is calculated as the log of 10,000 over 10 of 1,000 over 10, which equals 2. The TF-IDF score is the product of these quantities, so 0.03 times 2 is 0.06. Several other pre-processing steps can be used to get a meaningful list of words and their counts or frequencies. Words can be single words or bigrams of words. Bigrams are groups of two adjacent words, and such bigrams are commonly used as the basis for the statistical analysis of text. Bigrams can be extended to trigrams, 3 adjacent words, and more general, n-grams, which are sequences of n adjacent words. Section 19.1. The inverse multinomial logistic regression. In the following example, we analyze text information that comes from restaurant reviews. The text from a corpus of 6,166 restaurant reviews was reduced to 2,640 bigrams. We treat the 2,640 bigrams as the G possible outcome categories of a multinomial distribution. Each of these 2,640 probabilities is modeled as a function of covariance. In the restaurant review example, we have just one covariate, X, namely the overall restaurant rating on a scale from 1 to 5. But there may be more covariates, such as ratings on multiple categories that relate to food, service, and attractiveness of the restaurant, the price of a meal, the restaurant's location, and so on. In multinomial logistic regression, we model the probabilities through the P of K, which is equal to the probability where Y equals K, which is the exponential of alpha sub K plus X times beta sub K, which is over the summation of H equals 1 through G, of the exponential of alpha sub H plus X times beta sub H for K equals 1 through G, where G is 2,640. Note that the multinomial logistic regression representation leads to two times g minus 1, which is 5,278 coefficients. It becomes clear that one needs penalty-based estimation variable selection methods for the estimation of these parameters. After obtaining the estimates, we use the fitting results for the inverse prediction of x. Example 1, the restaurant reviews. We are given 6,166 restaurant reviews with counts on 2,640 bigrams. Each review has an average of 90 words. Furthermore, each review is accompanied by several ratings on a 5-star scale, an overall rating, and separate ratings for food, service, value, and atmosphere. For the following discussion, we use only the overall rating. So the text is here, and we can get the dimensions, which we already knew was 6,166 restaurants and 2,640 bigrams. We get the words, the terms, and how many times they have been used. And now we check the ratings, where we see what the overall rating was, from 5 to 1. We get to know what's in the matrix by doing the minimum count over the reviews over bigrams and the maximum count. A certain bigram in a certain review was mentioned 13 times. And here we look at the frequencies of the bigram in the column 1000. The data are extremely sparse. We will next check the overall rating, which is what we're mostly discussing. We determine frequencies of the 2,640 different bigrams, and this will take some time because it takes the computer a few minutes to process. So the analysis per review, we determine the frequencies of bigrams per review, and this will also take some time. Before we saw that really good was mentioned 251 times, and 10 times is the minimum. We get this plot. The multinomial logistic regression and the fitted reduction can be done where the bins is for faster inference if covariates are factors, and a covariate is a factor with 5 levels. We do the estimates of alphas and the estimates of betas. Then we do the fitted counts for the first review. Following provides fitted multinomial probabilities, which is the predicted multinomial probs for review 1, and we have to add 1. Then we do the same thing for the first 10 reviews. We get it to be 0.7, and we can create a box plot where the procedure works. Predicted ratings increase with actual ratings, and the questions to cut off, which cutoff to use for excellent review. We plot the information and we check its sensitivity. The sensitivity is 0.8, and then we do the true negatives, and it's also 0.81. And 0 might be a good cutoff. Sensitivity of the true positive rate is 0.89, and the false positive rate is 0.19. If the inverse prediction is greater than 0, we conclude the overall quality rating of 4 or 5. The score on the inverse prediction helps us assess the overall quality rating of a review. The box plots of Predin against the overall rating shows this quite clearly. The ROC analysis tells us about a reasonable cutoff on Predin that separates good reviews, those with overall ratings 4 and 5, from negative reviews, which are 3 or lower. A rule that classifies a review as positive if the inverse prediction is larger than 0, and as negative if the inverse prediction is smaller than 0, makes for an excellent decision rule. 89% of positive reviews are identified as positive, and 81% of negative reviews are identified as negative. One can use this rule to classify new incoming reviews. Using its bigram counts, we determine its inverse prediction. If the inverse prediction is greater than 0, we classify the new review as good, where the rating is 4 or higher. We move on to the next example, which is political statement. We're given text information on political speeches made by members of Congress. Genskow and Shapiro summarized the text of 529 members of Congress through 1,000-word trigrams and their associated frequencies. Furthermore, they collect the Republican vote percentage in the Speaker's district from the last election. This is an important variable as it represents the political ideology, the conservative or liberal leaning of the Speaker. We have to put in the Republican vote share, and we have to get to know what is in the matrix. A certain trigram is mentioned by a certain speaker 631 times. Here we can look at the frequencies of bigram in column 1000, and we do the multinomial logistic regression and fitted reduction, where we have to put in the estimates of the alphas and betas again, and we do the fitted counts for the first rep. The following provides fitted multinomial probabilities and the predicted multinomial probabilities for the first rep. Then we do the predictions of the inverse prediction, and we print the predicted ratings for the first 10 reps, and then we plot. The correlation between the predinv and the representative share is 0.6748. And the linear model has the coefficients of 0.4 and the predinv is 0.3. We can plot that and create a line. A scatter plot of the Republican vote share on the inverse prediction with the least squares fitted added shows a linear relationship. Assume a new text leads to an inverse prediction of 0. This value implies that the unknown Republican vote share is about 0.4. We would conclude that this text comes from the liberal side. An inverse prediction of 0.6 implies a Republican vote share of about 0.6. This would tell us that the text comes from the conservative side. A threshold of about 0.3 on the inverse prediction represents a good cutoff for deciding whether a certain text has come from the conservative side. Then we go to the appendix, which is the relationship between a Gentzkow and the Shapiro estimate of slants and partial least squares. The analysis conducted by Gentzkow and Shapiro is actually slightly different. They consider an ordinary regression, not a multinomial logistic regression, of the relative frequencies of trigrams on the vote shares that they then use in a second step to determine the estimate of the political slants of each representative. Their approach is as follows. We consider the matrix of phrase frequencies F equals Fij, where I equals 1 through n is the number of rows or representatives, and j is 1 through p, the number of columns or trigrams. The Fij are relative frequencies with counts normalized by the row sum. For each trigram, regress the phrase frequencies column j of the F matrix, which we denote here by Fj, onto the covariate x, here the Republican vote share. If Fj equals Aj plus Bjx plus the error term, and obtain the intercept Aj and slope Bj for j equals 1 through p, then subtract the intercept Aj from each column of frequencies in F, and for each row I, regress the row of this new matrix Fij minus Aj on the Bj. The estimate of xi in the regression, Fij minus Aj, equals xi bj plus error term of j, is a slant of row I. From elementary regression results, we know that the slants are given by xi hat equals the summation of j equals 1 through p of bj times Fij minus Aj over the summation of j equals 1 through p of bj squared for I equals 1 through n. It is not difficult to show that for standardized relative frequencies with mean 0 and variance 1, the slants are the fitted values in a partial least squares regression of the vector x, the Republican vote share. On the matrix of phrase frequencies, F equals Fij, using just the first partial least squares direction. So we'll code it again, and now we will use the slant. So we get a higher correlation between the slant and the covariate x, the Republican vote share. Standardization helps because we have 0.5666. Using PLS on the first partial least squares direction, scaling false means unstandardized relative frequencies are used. And we get 0.574, not the same as the slant on unstandardized relative frequencies. And then we will do the first partial least squares direction, scaling true means standardized relative frequencies. And we get 0.5666, which is the same as the slant on standardized relative frequencies. Lastly, we will do the same for the first partial least squares with standardized relative frequencies. It's the same as with Texter with scaling true, and the same as slant on standardized relative frequencies. This shows that with the standardized relative frequencies, the slants and the fitted values from PLS on the first partial least squares direction are identical. Note that the equivalence holds for standardized relative frequencies, but not for non-standardized relative frequencies. The slants that use non-standardized relative frequencies are not the same as the fitted values from the PLS1 on non-standardized relative frequencies. The PLS approach, which obtains an estimate of the slant, the fitted value of the covariate from the results of an ordinary regression of phrase frequencies on the covariate, and the inverse multinomial logistic regression approach, which starts from the notion that language is caused by ideology and then inversely predicts that ideology have much in common.